listen, I'm saying today we're still doing transformations of the two-pair functions. Monday we start doing other kinds of rational functions. They don't look like these. And so that's all this represents. The transformations are the two parents. By the way, this is a tree in a pot that's suspended above the ground. And so you can see the cables holding it up and stuff. That's rather remarkable. I want one. All right, look at this. These are not in graphing form. We just need to transform it into graphing form. This one's easy. The denominator can be rewritten as x minus 3 squared, which means it's 1 over x squared shifted to right 3. Yes? So let's just draw this real quick. Shift the origin right 3, put your new vertical asymptote, and then draw it here. So up 1, right 1 on that side. Exactly. Yeah, so these 2 points are not accurate, then you lose credit because that's how you showed that there's vertical stretch. Okay? And the horizontal asymptote is still y equals 0, the x-axis. Vertical asymptote shifted right 3. There's that. The main still excludes 3 now instead of 0, like the parent would have. The range is still everything above 0. Now, as for the intercepts, the y-intercept we'll have to calculate. It's easy. You just plug in 0, right? And if you plug in 0, the denominator becomes negative 3 squared. I'll put it down here. And that becomes 1 over 9, which makes sense if you look at our graph. The x-intercept, you can tell there isn't one from the graph, but I want to show the algebra. That thing equals 0. And watch, if you made this 0 look like a fraction, then you can cross multiply. This way you get 1, the other way you get 0. Well, 1 will never equal 0, therefore that will never equal 0, and therefore there's no x-intercept. But you don't have to show that. If the graph has no x-intercept, then just put none, and it's okay. Okay. But yeah, that's what I'm saying. You don't have to prove it. You don't have to show the work. But you should be able to. Yeah, there's nothing below the x-axis, right? All right, next. What do you notice about this one? Common factor of 2, right? Yeah. So I'm going to go and start by rewriting it with the 2 factored out, which means you could cancel. You get 3 there, and so you get 3, and the denominator is now x plus 1 squared, right? Or you could have realized from the get-go that this original had a common factor of 2 everywhere, and just cancel 2 out of everything, and get to the same results that way. Okay? And so it's shifted left 1 with a vertical stretch by a factor of 3. 1, 2, 3. So this point here and here is how you show whether it's stretched or not. And this time we're not going to calculate the intercepts because obviously it doesn't have an x-intercept and a y-intercept, obviously 3. Although just for the record, if I plug in 0, the denominator becomes 1 squared is 1, and 3 over 1 is 3. So you should be able to calculate it. And the main doesn't include negative 1. The range is everything above 0 again. And we already said no x-intercept, and the y-intercept is 3. And frankly, we're not going to graph all these. When we get to the end, we'll just focus on the algebra because the graphing part is pretty straightforward. All right, ready? Now, well, you realize it just changed because this is now an improper function. The degree is 1 on top and bottom, right? Which is improper because they're supposed to be smaller than the top. The previous ones, by the way, like this one, was degree 2 in the bottom. What was the numerator? And so that's proper to have a lower degree on top. And then likewise here, it's degree 0 to degree 2. That's also proper. Take out yesterday's note sheet and look at the back of it. It has the rules from Algebra 2 about how to figure out the horizontal asymptote. And the first rule says that if you have a proper rational function, then the horizontal asymptote is the x-axis, y equals 0, always. Which is what we saw in these, isn't it? So 1 and 2 have y equals 0 as the asymptote. Then the second rule says that if the degrees match, the degree of the numerator and denominator match, it's improper, but that kind of improper, then you find the asymptote by simply dividing that leading coefficient by that leading coefficient. So we should have a horizontal asymptote of y equals 1. And then the last rule says that if the numerator has a higher degree than the denominator, then you don't have a horizontal asymptote at all, you have oblique. But we won't be dealing with that yet because we're dealing with parent functions. And they have horizontal asymptotes. Now listen to me. Those rules from Algebra 2 are a nice backup. Keep them in mind, but what I'm saying is we are always going to do long division and to rewrite something that's improper. Okay? Okay. Actually, in this one, I'm going to do long division. Number 4, I'll do synthetic because I can. But here, long division goes like this. What goes here? And then you get x plus 5. When you subtract, you get a remainder of 1. Very short and easy. So this can be rewritten as that quotient plus that remainder over the divisor. And so there you go. Now you can see that's graphing form. It's the other parent, the reciprocal function. Shift to left 5 and up 1. But if you prefer, you can put it as 1 over x plus 5 plus 1. Thinking, I don't care. So, yeah. Mm-hmm. Now I'm saying that the long division is what gives us this. This is a horizontal asymptote. And you could have known it was going to be that by that little rule from Algebra 2. You just divide these coefficients. But really, we'll do the long division here to get the graphing form. I don't know if I answered your question, but and this one's a different parent function. So on the right, you go up one, right one, and draw that branch. On the left side will be below. Left one and down one. Of course, the domain does not include -5. The range is different now because it's everything except for 1. Yes? Now, for the intercepts. Listen, and of course we can see the x-intercept, appears to be -6. But I want to appreciate the fact that when you go to calculate those intercepts, you now have 2 forms of the equation to choose from. You can use whichever one you want. I prefer using this form, the original form for the intercepts. It's just faster and easier. So here, come down here, and we'll do x plus 6 over x plus 5 equals 0 to find the x-intercept. And over here, you'll just plug in 0, which of course that's just 6/5. Actually, about the y-intercept, look at over here. Look up here for a second. If you plug in 0 here, you get a 5th, and you get 1 and a 5th. It's the same thing, right? So for the y-intercept, I don't know if it really matters. I kind of like the 1 and a 5th. So you can see it should be just above 1, which is what our graph looks like. I forget about the vertical offset by the way. All right, lastly, listen. I want to understand again. You're trying to figure out when this fraction equals 0, and a fraction equals 0 exactly when the numerator equals 0. What happens when the denominator equals 0, by the way? The whole thing's undefined. So don't worry about that. You want to figure out when the numerator equals 0, which is when x is -6, which is what we saw in the graph. I'm just saying, you need to get that algebra, because you're going to be doing that a lot. Yeah, yeah. And like I said, you can write it as 1 plus, the constant's 1. So there. You can write it like that, or you can write it as this plus 1, which helps you see that it is a shift up 1. Now, this one, I'm going to do the division synthetically. We're dividing by x plus 3, so we put a minus 3 there. And the dividend is x plus 1, so you put a 1 for the x and a 1 for the constant, right? It can be really quick. Bring down the 1, multiply by negative 3, add, and that's your remainder, which means that's your quotient. The quotient is 1. Plus the remainder over the divisor. For one thing, you could have done long division, but synthetic division works too. They're both pretty short in this. And we really tend to prefer, we tend to write it like this. I'll take either one. Now, it's definitely shifted left 3. Is it shifted up 1 or down 1? Yeah. And watch, another way we could write it is with the two terms switch. I decide between saying switched and swapped, I almost say switch. But yeah, it's a vertical shift of positive 1. So yeah, go left 3, up 1. So your new origin is there. And then you got the vertical stretch and vertical flip. So on this side, you normally be up 1, then it's 2, but it's down 2. On the other side, it would be below instead of it's above. To that side, I'm just going to go and draw that branch. But actually, on the other side, I'm going to wait because I want to get the intercept first this time. I'll do that algebraically. First of all, what is the y-intercept? When you plug in 0 here, what do you get? 1/3, right? Here, hold on 1 second. If I plug in 0 here, by the way, I get 2/3 there, but 1 minus 2/3 is a third. The y-intercept is definitely a third, so put a point there. Good question? Exactly. And once again, that's why we always put that point there to show whether it's normal or vertically stretched. Now for the x-intercept, once again, set the whole original version, that equal to 0. So x plus 1 over x plus 3. You want to know when that equals 0, and that equals 0 exactly when the numerator equals 0, which is when x is negative 1. So x-intercept is negative 1, it turns out. Now that you know that, now go and graph that branch. And the rest should be easy. The coordinate lesson code is 1 for graphs moved to negative 3. The main range on this is a little, I guess we can do it one more time. Because I feel like we know it. In fact, the rest of this time, somebody just can do the algebra. Not like we're doing any more graphing at all. But we'll go and finish this one later. And the range is everything except for 1. All right. All right. This one's going to be a little different. But if we're going to do division, we need to do a long division. And there are a few options here, frankly, but I'm going to do the kind of the standard approach, which is just do the long division, which isn't hard, actually. Well, it goes here. And you can multiply it by 1, you get this. And when you subtract, you get a remainder of 1, and you're done. And it's easy. And so our function can be rewritten as the quotient of 1 plus the remainder over the divisor. But the divisor actually can be written as x plus 2 squared. There you go. You have graphing form. Which we're not actually going to graph or write anything else down. I just want to do the algebra for you. So let me show you another approach. That's graphical that we're after. Another thing you can do, watch this. And I could have done this in the previous problem too, like 3 and the same thing. What I'm going to do is I'm going to split this fraction up into 2 parts. Okay. First of all, I'm going to split the numerator into one part that matches the denominator, and then another part that doesn't. That is just whatever's extra. So in other words, I took this and split it up, and basically split the 5. Put a 4 with the rest of it, and the 1 I put over here. And then I can rewrite that as 2 separate fractions with that over that same denominator. And before I proceed, let's go backwards. If I gave you these 2 fractions, because they have a common denominator, you could add them. If you did add them, those would add up to the numerator we started with, wouldn't they? Okay, you can do that. But why did I do that? Because this part is 1. And this part is the other. And you're done. And so, watch. Number 16, no, number 6. I'm going to take that same approach in the long division. I'm just going to go and split it into 2 fractions right from the get-go. And so I'll take this numerator and split it and put the part that matches the denominator there, and the extra 2 I'll put over there. So it turns out to equal 1 plus 2 over x minus 5 squared. Is that better than the long division? Not necessarily. And it's about the same amount of writing, I think, but whatever. Okay? The long division is always going to work. So, it could get problems like this, certainly, they can get tricky. And so I'll put it this way. If you attempt this and it just isn't making sense, then just don't worry about it. Do long division. And so I really don't want to dwell on it. So we're going to move on. Exactly. All right. This is your number 8, actually, right? We're going to do this. We'll do this one first. Okay, tell me. We're trying to get y by itself. And the first thing can't be division. So what should we do first in this again? You have to come factor y, and so you factor it out. Listen to me. We've dealt with the situation before. The situation is where the variable you're trying to isolate is mixed in all through it. What do you do first? Get all the y terms on one side, which they've already done for us. Why do you get them all together? So you have a common factor that you can then factor out. And so, yes, factor out the y. So you can now do what? Divide by it, because now it's a factor that you can divide by. And we're done. Although you can write it like that, we prefer it written like this. Either way is okay though, okay? Now, this one's not the same at all. What should you do first here? Really, the easiest way is to go and divide by x. But you're trying to get y by itself, aren't you? So just strip everything away from y. So divide by x and then add 2 to both sides, you're done. Now, I want to show you the other approach, which would be to distribute the x. Not wrong. It's slower. But watch this. So distribute the x, you get this. You're trying to get y by itself, so move the x term to the other side. Let's put it first. It becomes a plus 2x, so you get that. And then you divide by x. You get 2x plus 1 all over x. Now, you could do long division, but really, since it's a monomial, you really just divide, like here, I'll just split the fraction. And this becomes 2, and that becomes 1 over x, and you get the same place. But it's more work. You're more likely to make a mistake, so just don't. Okay? Just, like I said, strip everything from y. Divide by x, add 2, boom, you got it. All right. And we are done, actually.